Can you see my screen?
Yes, yes.
Okay. So in the last session, we have covered the quantum states and how do we define the quantum space, quantum state, and why do we need quantum gates? Why don't we use classical gates? We also covered the visualization tool to define the states. Now we will be going through the quantum gates. So let's start with the single qubit gates. So first set of gates I will be covering is polygates. So there are three gates in the polygate, that is X gate, Y and Z gate. So let's see what is X gate. So what does this X gate do? It flips the qubit. That is, suppose you have the state of the qubit as 0.
Ma'am, please
It
put in slideshow mode, ma'am.
Sorry,
We can put in slideshow mode. The
it is.
presentation in slideshow mode. It is not in slideshow mode.
You cannot see in slideshow. Actually, I have already put. Wait.
Okay,
No,
ma'am.
we can't see in slideshow version. It's not in slideshow. I think
Now,
you'll have to reshare.
yeah, yeah,
Just
yeah.
reshare your
Yes.
screen and then.
Can you see now?
Yes, Vaishnavi.
Okay. So, where we were. So, what X gate does is it flips the qubit. That is, suppose if you have the initial state as 0, you want to make it into 1. So, we will use X gate. And in terms of visualization in block sphere, it is the rotation of 180 degrees about x-axis. So I'll show you in a minute. So this is the matrix representation of X gate, that is 0, 1 and 1, 0. And in terms of bra and ket, you can write this equation as ket 0 bra 1 plus ket 1 bra 0. So this this matrix you can look at in a way that suppose you write initial state as 0 here and initial state as 1. So if you have initial state as 1, you will get output as 0 1. That is one state. Suppose you have input as 1, that is initial state is 1, you will get the output as 0. That because X gate flips the qubit state, so you will get 0, that is 1 0. Representation of 0 state is 1 0 in terms of vector. Representation of 1 state in vector is 0 1. So you can see this equation as this is the input you have as 0, and the output you will get it as 1, plus if you have input as 1, you will get output as 0. So let's see how does it affect in terms in a matrix way. Suppose you have applied X gate to the 0 state, that is our initial state of the qubit. So what is X? That is 0, 1, 1, 0 in matrix form. And what is get 0? It is column vector of 1, 0. So if you multiply this, 0 plus 0 is 0, 1 plus 0 is 1. So what you have got output here as 1. So whenever you want to flip the state of the qubit, you use X gate. So I have written this in a simple way that when you apply X gate to the 0 state, you will get 1. And also when you apply the X gate to the 1 state, you will get 0. And you have the eigenvalues as 1 and minus 1. You It must be covered in the previous class how to find the eigenvalues and eigenvectors. So I have just written it directly. For X gate you have eigenvalues 1 and corresponding eigenvector as plus state, and for minus 1 you have eigenvector as minus. So let's see next gates, that is Y and Z gate. So as I told you about X gate, it is rotation of 180 degrees about X axis. Similarly for Y gate it is 180 degree about Y axis, and also for Z gate it is 180-degree rotation about Z axis. I haven't written this, but for Y gate it is about Y, and for Z it is about Z axis. So in matrix form, we write it as Y gate as 0 I minus I 0. So you can imagine this. Let's take I outside. If you take I outside from this, you will get I times 0 1. And here, if you take I outside, you will get minus 1 0. So what this Y gate does is, when the initial input is 0, that is, I told you this is input 0 and this is input 1. So when you have initial state as 0, if you apply Y gate, you will get one state but with I multiplied to it. And when your initial state is 1, you will get 0 state but with negative sign and I multiplied to this. So it is written the same way. Actually, this should be reversed, but that's fine for now. If suppose you have 0 as input, you will get 1 as output, but with I. And if you have 1 as input, you will get 0 as output, but with negative I. So similarly, what Z gate does is, when Z gate is applied to the 0 state, it does nothing. That is, when you apply Z gate to 0 state, you will get output as 0. When you apply Z gate to the 1 state, you will get 1 state but with negative sign. So I have written this in a simple way that when Y is applied to 0, you will get state 1 with I multiplied. And similarly, when it is applied to 1, it is 0 but with negative sign. So Y gate actually similarly acts as, flipping the qubit but with sign change and also the complex multiplied to it. But in case of Z gate, when you apply Z gate to the 0 state, it does nothing. But when you apply to 1 state, it also gives the 1 state but with negative sign. And you have the eigenvalues, that is 1 minus 1 with eigenvector as plus I and minus I. And for Z gate, you have eigenvalues 1 and minus 1 with eigenvectors as 0 and 1. So from these three gates, you must have observed this plus minus. For X gate, you have eigenvector as plus minus. You have Y and Z gate, you have eigenvectors at plus I, minus I, and 0 and 1. So let's go back to the block sphere and see how we have defined. So for Z, you have basis states as 0 and 1. So they are also the eigenvectors of this Z gate. Similarly, for X and Y gates, you have for X gate, what we have got the eigenvectors as superposition of 0 and 1, also with plus state and as minus state. And also for Y, we have got these two states as eigenvectors. So you can say that eigenvectors basis of those axes are also the eigenvectors of those gates or those axes. So the next gate is Hadamard gate. So remember, for Hadamard gate, for making the state into superposition, you don't need two qubits. It is a single qubit operation. So, as you know, for X, Y, and Z gates, you rotate the qubit or you rotate the state of that qubit into 180 degrees. Right, from if you want to go from 0 to 1, you flip the qubit, you use X gate, and you make 180-degree rotation from 0 to 1 about X axis, like this. And if you use Y gate, again, you will flip the qubit by 0 to 1 with I multiplied to it. And also with Z gate, you will go from 0 to 1. So, but in for this Hadamard gate, this gate you cannot, take any of these three axes. What it does is it has an imaginary axis you can draw like this, and when it is called as the rotation of 90 degrees about X and Z axis. That is this X, also Z. So, you can see this line as in between this this Z and X. You have this line. So, how does this Hadamard affects the qubit? When you want to, when you apply the Hadamard to zero state, it will go to plus state here. When you apply Hadamard to one state, you will go to the minus state, that is end of the x-axis. So in matrix form, I have written as 1 by root 2, 1, 1, 1, minus 1. What is this 1, 1? That is, it is the superposition of 0 and 1. In these cases, you don't have both as 1, right? But in case of Hadamard, probability there is probability of 0 and there is probability of 1. That is, you don't have exact 0 state or 1 state, you have an intermediate state of 0 and 1. It doesn't mean that you have two qubits. It means that it has the state which is neither 0 neither 1, but it is superposition of both. So how does it affect? When you apply Hadamard gate to 0, it gives plus state. When you apply Hadamard gate to 1, it gives minus state. So when you want to make a qubit into superposition, that is, combination, or yeah, combination of 0 and 1, you will apply H gate, that is Hadamard. So the next gate is I gate. So I have written here that it does nothing. So you can get the question that why is it then useful. So in application of this I gate is that you just show at some point that this qubit is doing nothing at this point of time. I'll show you in the circuit later, but right now you can say it doesn't affect the state of the qubit or the time it takes to convert one state to another. So basically, it doesn't affect anything while transformation of the qubit from one state to another. So the matrix form, as you know, is 1001. That is, if you have zero state, you will get zero state. If you have one state, you will get one state. That is, when you apply I to the zero, you will get zero. When you apply I gate to the get one state, you will get one. So the eigenvalue for I gate is 1 and eigenvector for I gate is 0, get 0 and get 1. So as you have seen, XYZ gates, they rotate about their own axis to 180 degrees. So if you want to rotate the state into 90 degrees, so this gate, what it does, it rotates the qubit state to 90 degrees about z axis. Remember this, about z axis. So S gate and S dagger both are different. So the matrix form for S gate is 1 0 and 0 e raised to pi by 2, and S dagger is 1 0 0 e raised to minus I pi by 2. So when you have initial state as 0, what S gate does, it does nothing. Similar for S dagger, but when you have state 1, it rotates the qubit to 90 degrees about z axis with state 1. Similarly, for S dagger, when you apply S dagger to the state 1, you will get state 1 with rotation of minus 90 degree. So I have misplaced this as minus pi by 4, but it should be minus I pi by 2. So let's take the next two gates, that is T and T dagger. So S gate was rotation about 90 degrees. Now, if you want to rotate it about 45 degrees, we use T or T dagger gate. So what they do, T gate rotates the qubit about z axis to 45 degrees. Whereas for T dagger, it rotates about z axis with minus 45 degrees. So what is minus sign? If in this um, quantum gates, we use positive rotation as anti-clockwise in the Bloch sphere and negative rotation as clockwise. So if this is minus, means you have to rotate the qubit in clockwise direction. You also have one property that S is equal to T square, that is T dot T. You can confirm this by multiplying T with itself, multiplying the vector of matrix of T with itself, and similarly also with the case of S dagger, which is equal to T dagger into T dagger. So you can just see from the angle that if you apply T gate two times, that is 45 plus 45 around z axis, it is same as applying the S gate once. So let's see the effect, how it affects that when you apply T or T dagger to the initial to the zero state, it does nothing. But when you apply this to one state, it will rotate about 45 degrees with state 1. So similarly for T dagger, when you apply T dagger to the state 1, it rotates about minus 45 degrees about z axis with the state output as get 1. So next gate is P gate. So this is more generalized gate. You know, you can define 4 gates from this P gate. That is, it is a parameterized gate, which means uh, you need to give some input to this gate, that is phi. So if you want to use this gate, you have to give input phi as something so that it gives some of these following gates. So what it does, it rotates angle of theta, which is real number, around z axis. So in general, if you want to rotate about any theta, you will use P gate. So then, suppose you have phi is equal to pi. If it rotates around z axis 180 degrees, what you will get? You'll get here minus 1. E raised to I pi is minus 1. So 100 minus 1 is z gate. So if you substitute phi as pi by 2, you will get s. If you set this phi as 0, e raised to 0 is 1. So you will simply get I. If you substitute phi as pi by 4, you will get t, that is e raised to I pi by 4. And you can also give input as minus pi by 4, you will get t dagger. So this is in general, if you want to use any phi other than these standard gates, you will use P gate. So I have covered this U gate while explaining the unitarity. It is the same gate. In general, I have written in terms in this gate, you can define only some of the gates, right? You can give phi as different, and you cannot uh, you know explain all the gates with the help of P gate. So but with the help of U gate, you can get any gate from wave by varying this theta, phi and lambda. That is theta, phi and lambda being rotations around x, y and z axis. So if you give the specific rotations around these axes, and then to get the desired output, you can form a U gate. So it is cos theta by 2 minus e raised to I lambda sine theta by 2, e raised to I theta sine theta by 2, and e raised to I phi plus lambda cos theta by 2. So I have taken one example here. Let's say I have taken theta as pi by 2, phi as 0, and lambda as pi. So what you will get, cos pi by 4, that is if you put theta as pi by 2, it will be pi by 4. Cos pi by 4 is 1 by root 2. 1 by root 2 is taken outside, 1. What you will get here, lambda is, what is lambda? Lambda is pi. E raised to I pi, as you know, it is minus 1, minus minus plus, and sine pi by 4 is 1 by root 2. So in all the 4 cases, you will get 1 by root 2, which is taken outside. And here I raised to e raised to I phi. What is phi? Phi is 0. So it is simply 1. And here e raised to I phi plus lambda, that is 0 plus pi. which is -1. So what you have got here, you have got H, that is Hadamard gate. So like that, if you vary theta, phi, and lambda such that you can get any gate which was defined earlier. So let me brief all the gates we have I have explained. I have explained Pauli gate, that is X, Y, and Z, which rotates about its own axis. And then I have explained about Hadamard gate, which is used when we want the superposition of the qubit state. And we have also covered P gate, which is called as phase gate or parameterized gate, which is used to rotate the qubit state into the angle which you want to give as input. And then you have defined the U gate, which is most general form of all the gates we have defined in the quantum computing, which is the U gate. So from which you can derive any gate which was discussed earlier. So now let's see how we will be uh, writing these gates in Qiskit. Can you see my screen?
Ah, yes, ma'am. I can see.
Okay. So you have defined the gates. Now you want to use the gates to get some output. Then we will be uh, going through the Qiskit, which is given by IBM. So I use Jupyter Notebook. So I will just go through how do we install this Jupyter Notebook. So what you have to do first, you have to install Anaconda, right? I'll just write it down here. Yeah, I will not show how actually we install it. It is very simple. First, you have to go to your browser and install Anaconda, and then you, with your OS, Windows, Mac OS, or Linux, you choose the OS you want, and then you install it. And the installation is very simple. You don't need extra guidance to install the Anaconda. The default settings will be enough to install this Anaconda. Then after installing Anaconda, you should go to the command prompt. Then you can type pip install Qiskit. So after installing the Qiskit, you will install all the libraries related to it, so that you can write the programs and write the circuits in Qiskit. After installing the Qiskit, next you can write as Jupyter Notebook in your command prompt. Then it will open this file. As you can see what I have opened, so you will get this file. You can make a new file and start writing your code. Or instead of going installing the Qiskit in command prompt, you can just open this uh, Python file, and then you can type here pip install Qiskit. So here also you can install the Qiskit. So after installing the Qiskit, you need to import the Qiskit. So these are some of the libraries I have imported. I will explain all this as we use them. So I have imported NumPy as NP, that is which is used to use the mathematical expressions such as pi. We have also imported some of the uh, backends, and some of to execute the circuit we have imported AR, we have imported quantum circuit, we have also imported the registers, that is classical and quantum registers. And to visualize the gates or the circuits we have made, we have also imported the block sphere, that is plot block multivector, from Qiskit.visualization. Also to draw the histogram, that is the probability graph of the states of the qubit, we have also imported the plot histogram from Qiskit visualization. And we have taken pi and square root from math. So to see the Qiskit version, you can type it as Qiskit version. So you will get the version of the Qiskit. And if you want to see the backends which are used in the Qiskit, you can use this as AR backend and basic AR backends. So basically, AR backends is written in C++ code, and whereas basic AR is in Python. So we have imported all the backends. You can see from this line, import AR and basic AR. So if you want to see what are the backends used, you can just type it as AR.backends. You will get all the names such as AR simulator, AR density matrix, AR matrix product state, AR simulator unitary, etc. So now mathematically how you can uh, you know uh, define the state. Now let's see in Qiskit how will you initialize the quantum circuit. So I have initialized a classical register as CR. CR is equal to classical register 1 with name CR. What is 1? 1 is being the number of the registers we want. I want only one classical register, so I have written one, and the name I want to display as CR, and QR I have defined it as quantum register, which is also one with the name QR in colon. And I have combined these two with the help of quantum circuit. That is QC is equal to quantum circuit with QR and CR. So what is quantum circuit? It is basically the ordered sequence of all the gates, all the measurements, and or you can say these are the set of instructions you give to the computer to execute and perform the operation. Then what you want to do, you want to draw the circuit. What after executing this cell, what you will get? QR and CR. You haven't applied any gate here, that is why it is just a blank line it is showing. And the single line shows that it is a quantum register, whereas the double line shows it is classical. So these 2 points you have to remember before forming the quantum circuit, that when you don't initialize any qubit, the Qiskit takes zero state, that is ket 0, as the initial state. If you do not suppose, let's say you have created two registers here, the state of those will be 0. State of this registers will be 0, because we haven't initialized the qubit, then by default it will take as 0.
Oh, classical register is a must to give, or we can have a quantum registers alone.
While defining it, you can give only quantum registers, but classical registers are used to measure these qubits. So to for measurements we use classical, and to perform the operation we use quantum registers. So the registers, why do we use the registers? Basically to store the information, right?
You mean to say classical registers are meant to store the states data
They are actually meant to store the data after measurement.
after measurement? So without classical register, then I can't create a quantum circuit.
No, right now no.
So I have to use both classical register and quantum register.
Yes.
So classical register to store the data after the execution and quantum register to perform the quantum operations on the data.
Yes, right.
Okay, okay.
Also, before going through the forming the circuit, you need to remember the Qiskit ordering. If you are using the Qiskit, if you let's say you have created three qubits, it will not number as q0, q1, q2. It will instead number as q2, q1, q0. That it has a reverse ordering. So you need to take care of this while making any circuits. So we will see this later. So we have covered first gate, our
On what basis we decide the number of registers? You say one or a quantum register with one value, or quantum or classical register with the one or two. How do we decide that?
it depends on what output do you want. Suppose you have three qubits and you have entangled two of the
That's what the
qubits.
3 qubits. How do I decide?
It depends, like how will you take three qubits or two qubits, like that.
Mm. So how will I know for my problem how many qubits I require for my problem?
So it depends upon the application, like what output you want or how many outputs you want, you can say. Suppose I give example, for C not gate, which is not covered yet, it is 2 qubit gate. There is requirement of two qubits. So two C not gate is used to entangle two qubits. So the condition to use C not gate is you must have two qubits to perform this operation.
Yeah, every gate requires its own defined inputs. So based on that input, we decide the qubit for the gate.
Yeah. So right
Okay,
now I have covered the gates for only single qubit.
single bit. Okay,
Yeah.
single qubit.
There are
Okay.
gates which require uh, must be 2 qubits or
Mm.
must be 3 qubits also. So which
Okay. So
will
that
be
is for
covered in next.
gate.
Yeah.
But here in the register, when I give the gate, how do I decide on that? Classical register you defined initially, with one, or quantum register with one. That how do I decide?
This is just to show you, but you can take any number of gates. It won't give any error. But
Okay.
suppose let's you if you take three classical
Mm.
here and three quantum, no problem. Because but see, if it depends on how many of them you use it. Suppose
That is what.
you
Mm.
want to flip the qubit. How many qubits you want to flip the state of only one
Mm.
only one qubit. So if even if you take two qubits, you are going to use only one output, right? Output of only one qubit.
Mm.
So it is unnecessary to use you just take qubit without performing any operation. So that is just takes more
So that
space.
registers qubit also has to be decided based on the gates that I use.
Yeah, and also based on the output or the application you want.
And both classical and quantum can have the same number of qubits.
Yes, no. The quantum is qubit and the classical is our normal classical register.
Register. So, but if I give quantum 3 qubits and classical, how much I have to give? The same three, or I can give any number?
Yeah, so let's say you have three qubits.
Mm.
Okay, you have applied some operations, you have done some entanglement, superposition you have done on these three qubits. But at the end, what you want the output of only third qubit. Okay, let's say you
Okay.
want output of only third qubit. Then how many classical registers you will use? You will use only one classical register. You can
Okay.
define three, but rest will be of no use. So you can define
Okay.
only
So
one
it
class.
is like our array definition in our programming code. I randomly gives a int of 10, int A of 10 or B of 10, like that. So 10 locations will be allotted for the storage of data. In the same way here also, I can randomly give some values for my qubits and my bits requirement.
Yeah, yeah.
Okay.
So
Okay.
as you know, in quantum, space is or any for any uh, electronic system,
Mm.
the space is very
Mm,
uh,
mm.
important point. So if you just take it and which is of no use, it simply takes more space, right? So
Okay.
yeah. So right now at this stage you can take any. It doesn't harm your.
With low, small number, no issues. But then with big number, wastage of memory will be there. Okay,
Yeah,
fine.
yeah, yeah.
It
Right.
involves cost as well. Fine.
Yes, yes. Right. That's what.
Okay, okay, okay. But then for understanding of these gates, we can work with simple problems, but actually their purpose is not for these simple problems. Is it right?
Sorry. Can you repeat?
For understanding the working of these gates, we can
Mhm.
apply them in a simple mathematical problems and understand how they work.
Yeah, you can change all the number of uh, gates. You define it without even using them.
Okay, okay, no problem. Yeah,
Yeah.
please proceed. Okay, okay.
Yes. So here, in this case, what we have defined, we have defined the classical register as well as quantum register. But let's say you just want to flip the qubit, you don't want to measure what is its output. So even if you don't define the classical register, it is not an error. So here, what I have done, I have defined the quantum register 1, which is QR, named QR, and I have prepared a quantum circuit only with the help of this quantum register, that is QRX. And I have prepared this QRX. Its initial state will be 0. Then what I'll do, I'll apply X gate. How do you apply the X gate? Name of this quantum circuit, that is QCX dot X. So to apply X gate, you will just use dot X, and inside that you will use on which qubit you want to apply. That is, in this case, it is only one qubit, but how you will write QR of 0. That is, on this register, you want to apply the gate. What is the 0? It means 0th qubit. So the numbering starts in the Qiskit as from 0. So you have written QRX of 0. What does this mean? It is like you have list of qubits. That is, suppose I have written here as 6. So 6 number of qubits are there. If you want to apply X gate to the first qubit, you will write QRX of 0. If you want to apply X gate to the fifth qubit, you will write QRX of 4. So then you will draw the circuit as QCX dot draw. So after executing, you will get this circuit. That is, this is the visualization of X gate. You have applied the X gate. You haven't done any measurement. That is why you haven't defined the classical register. So let's plot this X gate in the block sphere. You have learned block sphere. Now let's see how you can, after applying the gate, how does this block sphere look like? So we are using the backend as AER, state vector simulator as backend. So how do we get that? We will write it as AER dot get backend in the bracket state vector simulator, and then we will define assign this to the backend. Then we will get the result of this backend by executing this QCX. What is QCX? Our quantum circuit, not register. QCX. I have given input as QCX. Execute this circuit into our backend, that is state vector simulator. What is simulator? Why do we use simulator?
uh, is to visualize it in a simulation. Huh? I don't know. And what do you mean by this AER actually?
Actually, we are, see, I have shown here the backends. This is just a way to, using the backends, AR dot backend. So these are all the backends which are available. So depending upon what we want to what we want the output as, we will use all these backends. So which one we have used? AR state vector we have used, right?
Here
This,
also, how do we get to know which one I have to use? I
yeah.
can also
Suppose,
go for first one AER simulator itself, no? So otherwise, how will I know which one I have to use?
see, I have told you, I have defined the matrix of all the gates, right?
Hmm.
So those are unitary gates of those sorry, those are the unitary, matrices of those gates. So suppose you want to I have also defined the density matrix, right? Rho is equal to the outer product of that state with itself. So that is actually a matrix. Suppose you want a density matrix of any vector or any state. You will use what you'll use? You will use this density matrix simulator.
Okay.
So if you
So
want
for the current one, you are using AR simulator state vector, right?
state vector. So what is state vector? By name only you can get. What do you want? Which vector do you want? State. You want the state
Okay.
of that uh,
Okay. Okay.
circuit. Yeah. So that is
Okay.
state vector.
Mm. So the present state of the qubit I want to know, so I just make use of the state vector then.
Yes. Yes.
Matrix product being the and the simple one AR simulator is
It is in general.
general one.
Yes.
Okay. So now we saw polygate, right?
Yes. We are in the X gate, which is polygate.
Polygate, and you are using the block sphere, wherein you are calling this backend state vector simulator.
Yeah.
Simulator.
So to
Okay.
give output to the block sphere, what do you want? You want the state of this gate, state of the circuit, no? So you are giving input to our block sphere as when you want to visualize what block sphere asks is, I want what I want. I want the result, right? So give me the result. I will show you in visualization. So that is what we are doing. So to give the output to this block sphere, what we are doing, we are giving the this block sphere our result. So how do we find that result? By sending our circuit to our backend to perform this operation. So this looks very simple, but you for any circuit to get the output, you have to send this circuit to the backends.
Okay.
So now we will get the result. We have used this backend, and then we have used the this result as execute qcx in this backend, then dot result. I want a result of that backend after sending this into the backend. And then what I want the state vector from this result. So how do you define it? Dot get state vector qcx decimal equal to 3. That is, whatever the number you get, it will round off to 3. That's it. So you will, yes,
Yeah.
okay. So if you want to print the state, don't worry, for first time you won't understand all these terms. So I'll explain 2 3 times for the gates, then you will get familiarized. So I will print the result. I want the state vector of this circuit. I want the output of the circuit in terms of vector. And to plot it into the block vector, what I have done, I have given input as my result to this block vector. That is, I'm calling this as plot block multivector, and I have given input to this vector as result. So after executing this, you will get the quantum state is 0 plus 0 ij and 1 plus 0 z. So by default, the this Qiskit will take every state as complex space. It will define it in terms of complex. If the complex term is 0, then it will just show you that 0 j. So it means it is just 0 1, right? So what is 0 1? What is 0 1? It is get 1, right? That is state 1. So you have applied, first your state was 0, then you have applied X gate, then what you should get output as 1, right? You have got the output as 1. So in vector form it is written as 0 plus 0 and 1. So after executing this line, what you will get, the vector is pointing at 1. So first this state was here like this, and after applying the X gate, what X gate does, it rotates to 180 degree about X axis, right? So it has rotated about X axis from 0 to 1 in anti-clockwise direction. That is like this. So printing the unitary operator for poly X. What is unitary operator? We have already defined it, right? When you have input 0, you will get 1. When you have input as 1, you will get 0. So we are using the simulator as unitary simulator. So we are using the backend as AR.get backend unitary simulator, then execute the circuit by giving the execute command, execute this QC on this backend, and then result. Get the result of this unitary, that is X unitary dot result, and of that result you want the unitary matrix, that is get unitary of that QCX with decimal 3 units. So what you have got the output 0 1 1 0. So you have defined it. Can you see my slide?
No, still it's in the Jupyter notebook only.
Okay, okay. Just a minute. So we have defined this here, right? For X gate, if you have input 0, you will get 0. This is the unitary gate I have, executed there. 0 1 and 1 0. Now let's perform the measurement. So when you perform the measurement, you need classical registers. Then I have defined this CRX as classical register. One classical register I need with name CR, and one quantum register, one number with name QR. Then you have combined this into as quantum circuit with the input as quantum register and classical register. So here you should remember that first input will be the number of quantum registers you want, and the second will be the number of classical registers you want. Then what is next? You have applied the X gate, and then how to measure this X gate? QCX dot measure 0 0. What does this mean? Measures this 0th qubit into the 0 classical bit. So if you draw this circuit, how you will what you will get? You have measured this a quantum register, that is QR, in this classical register, that is 0 and 0. So what value does it give after measurement? It will give result as 1. So let's now we have got we now we know how to make a circuit from the registers, and we also know how to get the state vector. Now also we have taken this unitary vector out of this circuit. We also know that how do we measure the circuit by just giving the command as measure.
Is unitary is a must that we have to use, or we can use only Pauli and then finish it?
Sorry.
No, actually, this code is to understand how polygate works. Huh?
Yeah.
How polygate is like our the classic NOT gate. Whatever input you
Yes.
give, it will negate it and give.
Yes. Not negate. It
Hmm.
flips the state.
Flips. Okay. One
Yes.
means zero, zero means one.
Yeah.
Okay.
Negation
So,
means you can say in terms of Z gate. What Z gate does, if the input is 1, it will give -1. So that is negation.
correct, correct, correct.
Yeah.
Yes. Yeah. So
So
here, so if it flips, okay. So whatever the input is, uh, and we are representing that as complex number. Then.
yeah, by default, in when you execute any code, if your output is in general, your output will be float, right? In general,
Mm, mm.
yeah, you get, even if the output is 1, you will get 1.000. So just like that, here the default value is complex number. Even
Okay.
if this means 0, it will type it as 0 plus 0j. So it is
Okay.
basically means 0, right?
Fine,
Yeah.
fine.
Yes.
Okay. Okay. So this unitary, why we are introducing this unitary? Is it required, or without unitary itself we can work? Or unitary simulated, we are calling, no?
Yeah, it is not a requirement. It is just I have just showed you what is the unitary matrix of this circuit.
Mm. Uh, Unitary matrix is just matrix with all ones. Is it correct?
No, I have explained you unitarity, right? What is unitarity? Uh, you have prepared the matrix such that you will not exceed the probability 1, right?
Okay.
So
In terms of probability, yeah. Okay.
yeah, unitary similarly, it doesn't mean this identity matrix. So it
Uh, uh,
means you
uh.
have, created a gate such
Mm.
that it fulfills all the criteria of quantum gates. That is, it doesn't exceed the probability as 1, or length of that vector as 1.
Okay, so to I mean bring them within the probability of one, you're combining it with unitary matrix or
Uh,
unitary gates.
yeah, not combining, that is the unitary gate. Whatever we, define this X gate, Y gate, Z gate, those are unitary gates, which have, which satisfy the unitarity condition, you can say.
But,
Yeah.
but then poly X gate is not unitary gate then. It
No,
is an unitary.
it
It
is
is an
unitary
unitary.
gate. Yeah.
Ah, okay. Okay.
Yes.
Or as
All the
it is
gates are
in
unitary.
unitary gate. So in that case, whatever gates create, I have to use this unitary also.
Uh,
Unitary operator or whatever you call. That
yeah,
also to be used.
yes. I have it. This is just to show you the gate. It is not part of the circuit. It is not
Mm.
part of the circuit. It is just I have written the code to get the output as unitary
Mm,
matrix
mm,
of the circuit. Yeah. Suppose I have told you what is the X gate, right, as matrix, but let's say you don't know what is the unitary gate of that matrix, so you can call this simulator and execute run, and then you will get this 0110.
Zero, one,
That
okay.
is from this also you can understand, yeah, what the thing gives. What is this? What it gives is when you have the 0, you will get the output as 01. When you have 1, you will get the output as 0.
Zero.
So it flips it from this gate. Suppose you don't know the gate, you can just call this unitary simulator and check what this gate or what this circuit is.
Okay. Okay. So somehow I have understood. Okay.
Okay, is it clear?
Yes. When I work, I think it may be more.
Okay, let's see some more gates then.
Mm.
It will be
Yeah.
more clear. Again, if you don't have, then you can ask again.
Okay.
Yeah. Okay. So now you want the output after measurement. You want the what is the probability of that state when you perform this operation. So to see that, we again take this quantum circuit and uh, send it to the backend called Cosm simulator. So again, we have defined it as backend. We have got the backend as AR.get backend Cosm simulator. Then we have executed this QCX on the backend with shorts as 1000, and then you will get the result from this execution as this job dot result. Then you want to measure the number of counts, that is result dot get counts QCX. I'll show you what is counts. Then print these counts. So what does this mean count? You have defined here shorts as 1000, right? So as you know, the states are probabilistic. Sorry, the states are probabilistic. So when you measure it, if you perform the operation more number of times, it will give the proper result. So as I have defined, suppose let's say Hadamard gate, it says 50% of the time it gives 0 and 50% of the time it gives 1. So to understand that, you need to perform this operation number of times. So that's what the shorts means. So I have performed this operation 1000 times, and then I have got the result. You can perform it any number of times. I have just given it as 1000. Then you got the result from this execution. Then you have counted that result, how many times you have got that result. So to get the counts, you use result dot get counts of that circuit. So it will print the number of counts. So let's say the total counts we have received as 1000. of what? State 1. That is, you have given this circuit 1000 times to the backend, and then what it has given the output as 1 whole 1000 number of times. So that is the meaning of this counts. So let's say you have performed Hadamard gate, and then mathematically we know that 50% it gives 0, 50% it gives 1. Then what it does, out of 1000, 500 times it will give 0 and 500 times it will give 1. So that is the use of counts. So you count the result and with along with the state. So you want to plot the number of counts with its probability, then we use plot histogram of the counts. So if
Here the
you,
state had been only 1, na? It didn't go to 0. That's what it means.
yeah, because as this is X gate, when you apply this X gate to, 0 state, you know that the outcome is 1.
Yeah,
So
it
all
flips
the
to
time,
1. So,
yeah. So all the time it has given the output as 1. So this 1000, 1000 means the output is 1 all the time.
all the time.
Yes.
So this particular gate, we are trying to understand the flipping of qubits.
Yes. It is flipping of, yeah, state.
Okay, but here we don't have that superposition concept for this.
No, it see, if you want superposition, you use Hadamard gate.
Okay, so except Hadamard gate, rest all gates don't consider superposition of the qubits then.
Uh, Sorry, can you repeat?
So only using Hadamard gates, I'll be able to get the superposition of a particular qubit. Is it like that?
Yeah, yeah, yeah. If
So
you want
rest of the
superposition,
uh,
then
yeah, rest
yeah,
yeah, yeah, please proceed.
yeah. So if you want to flip, you use X gate. So you
So
just
it is
want
like
output
this.
as 1. So you
Mm,
use X gate.
mm.
Yes.
So in this, no superposition is there.
No,
So
no.
it's only flipping.
Yes. So
Okay.
as you can see, if you plot the histogram, uh, this is x-axis is the state, number of states, possible state you can have, and the probabilities of that state. Right. So let's say here what it has said, 1000 is number of shots and 1 is the output. What is the probability of 1 is 1. That is 100%, there is 100% chance that you will get output as 1. So for Hadamard gate, how it will show, I'll show it later, but how it will show, here it will show 0, it will be 1 here, and probabilities of both will be zero point 0.5, right? So this graph will come as two bars. Here for 0 it is 50%, for 1 it is 50%.
Okay. So when we are in need of superposition states only, you have to use Hadamard. Otherwise, we can use normal gates.
Yes.
So
So
I
these are,
thought
yeah.
all are quantum gates. So with every gates, we'll be able to find the superposition of the qubits. This is not. It's not like that.
No, no, no. If you want
So
superposition, you perform that, you apply that gate.
Hadamard. Otherwise, it works like a normal digital gate with
Yes.
the defined inputs and outputs. It will work.
Yes, yes.
Okay.
So later when you go to applications of these, later will be covered, you will be using Hadamard gate most of the times, because you
Hmm.
want to make the qubit into superposition. So I have explained all the gates. It doesn't mean you have to use all the gates. Depending upon what the output you want, you can use the gates, you can choose the gates you want.
Yes, understood.
Yes. So uh, I have showed you, last time what we have done. We have defined the quantum register, we have defined classical register, and then we have measured it, and then we got the circuit, right? So instead of that, there is another way to define quantum circuit, which you will be defining from now, because this is the easiest way. You can define it as a quantum circuit directly, and with input as 2 and name is equal to qc, which is optional. You can give if you want, or you can leave it. So what does this mean? It means you are giving input directly as 2 qubits and 2 classical bits. So instead of writing those 2 lines, 2 classical registers, 2 quantum register, you can directly give input to this quantum circuit, with first input as quantum qubit and the second as classical bit. So this makes it simple, right? Just one line. Then after writing this, you will the it will create 2 qubits and 2 bits. Then you apply x gate, that is qcx dot x of 0 directly on 0. So here how you had done for the last time, when you want to apply the uh, X gate or any gate to the registers, what is the syntax? You write the name of that register and the index of the register, right? Suppose here you have one or two, any number, you are giving name of the register and then it's along with its index. But in this case, when you directly form a quantum circuit with just input as 2 you can directly write it as qcx, that is this quantum circuit dot x of 0. What does this mean? 0 means zeroth qubit, that is you have total number 2 qubits, it will apply x gate to zeroth qubit. So this is what we have done. This is q naught, q1, and this is c2. What does this mean? You have classical registers, 2 classical registers. Then qcx dot barrier. So what does this do? It just it just makes the circuit in a good way. That is, let's say, it this does nothing. This doesn't consume any time or any space. It is just a nice representation, nothing more. So here we haven't given any barrier because it was just a simple circuit. But here we have given because just to look it nice. So let's say if you haven't given this measurement will be here and this will be here. So it doesn't matter if you give it or not, but it is just a nice way of displaying the circuit. So you will understand this later why barrier is used. So I have applied the barrier after applying quantum this gate, x gate, that is this, and then I have measured this circuit 0 0, which means I am measuring this 0th qubit to the 0th classical bit, and then I have also measured qc x dot measure 1 1, means I also want to measure first classical quantum bit to the classical bit. So I have measured both of the qubits to the both of the classical bits. So that is why we have taken classical bits as 2. So this is another way of representing the or forming the quantum circuit, instead of writing those two lines as quantum register and classical register. So in above case, what you have done, you have measured each qubit separately with each classical bit. Instead of writing these two lines, you can write it down as QC dot measure all. So what it does, it will measure all the qubits with all the classical bits. So instead of if you want to measure all the qubits, then instead of writing these two lines, you can write it as QC dot measure all. So this completes the X gate. I will explain Y gate and some of the gates. Then you can go through rest of the gates, as the code is very simple. You just have to write uh, as Y instead of X. So in this case, what we have done, uh, we have defined quantum circuit, that is QCY, quantum circuit 1 1. I want one quantum bit, one classical bit with name as QC. Then I have performed Y gate on 0th qubit. Then I have drawn the circuit. So I have one qubit, one classical bit with one Y gate applied. So how do we plot this Y gate? We call the state vector simulator. What we want as a output for block vector, we want the result, so that to display in the block sphere. So for result, what you want, first you want backend, which we have extracted as state vector simulator. Then you have executed this our quantum circuit, that is QCY, into this backend, and then you got the result from this backend. But from the result, you want the result in terms of state vector. So if you would want in terms of unitary, you can write it as get unitary. If you want state vector, we have written here dot get state vector QCY with decimal 3. So this is optional. So we print the result. What we got? 0 and I, right? 0 minus 0 j, and second one is 0 plus 1j. What does this mean? If you apply the Y gate to the initial state, which is 0, what you'll get? It flips the qubit with I multiplied to the one state, right? We have already, uh, we have already discussed this vector. So let's see, after giving the input as a result to this block vector, what you will get. It will give one state, right? But you cannot show the imaginary part in the block sphere, but it will all it has flipped the qubit from 0 to 1, but with I multiplied to this state. So this is also still not the superposition. We have still flipped the qubit with complex number multiplied to it. So now let's print the unitary operator. So we call the backend as aer.get backend with unitary simulator. Then we execute the circuit on this our circuit on the backend. Then we get the unitary matrix out of this result as 0 minus 1, sorry, 0 1 and minus I times 0, right? This is what we have defined the unitary matrix of Y gate, right? That is, when you have input 0, it will flip, but with I multiplied to it. That is the imaginary part. When you have state 1, you will get 0 state, but with negative complex number. So this is what we have already defined this vector as. That is, if you get the 0 input, you will get as 0 j. You will, if you have input 1, you will get minus j 0. So here uh, we have created just barrier between the gate and the measurement. Now let's run this on the COSM simulator. Basically, what simulators do is it gives it is just like a prototype and model. So what model gives, suppose let's say you want to build any building, and you just don't go and start doing making the building. You make a prototype of it, small model, and you see all the possible operations or any difficulties you get from that model, and then you go for real device. So simulators are just, it just shows what you will get the effect when you actually perform these operations on real device. So this is not actually on real device we are performing on. These are just simulators which are replica of our quantum computer. So we have used this COSM simulator, and then we have executed this again circuit with backend with shorts 1000, and then we have got the result. And from this result, you can extract many things, such as state vector. We have extracted unitary matrix, and we can also extract the counts. You, if you want to plot the graph in terms of probability, you uh, extract the counts from result. So I have extracted the counts from the result. Then in this case also, what received I have got the state 1 with all the time. Then if I plot this graph, so the probability of state 1 is 1 for all the shots. So now let's see how this Z gate behaves. So what I have done, I have applied the Z gate to the state 1. How is it state 1? Why I have taken this X gate? Because if you apply Z gate to the 0 state, it does nothing. But if you apply Z gate to the 1 state, it will negate the value, that is 1 to minus 1. So let's see how you can you can visualize this. So I have prepared this I have prepared this circuit, that is one quantum bit and one classical bit with X and Z applied. Why did I use this X gate? Because I want input as 1 to this Z gate. So to get the input as 1, I have applied X gate, and then I'm applying the Z gate to actually see the effect of Z. So when you get the vector, what you will get the vector as 0 minus 1. It doesn't flip the qubit state, it just negates the state. So when you plot this on the block sphere, it will give 1. So what actually happened here? You had one state and you have got the one state. So what does this mean? So why it doesn't show anything in the blocks here? Why? Because negation is what? Rotation about its axis. Uh, in the negative way, that is clockwise, you can say. So this one state has rotated clockwise. But let's say you have a ball, which is plain ball. You have kept it on the table, and then again after some time you have rotated that ball and again kept. It will still look the same, but actually it has done some rotation, so it is same like this. So it is the state 1, but it has done rotation about its own axis. So that is why we cannot see any effect in this block sphere. But to actually see the effect, what we are doing, we are seeing the about quantum state, that is state vector. So we actually know that it has rotated around its own axis. That is why the value here is -1. So unitary operator, about your of unitary of this Z gate. If you have state 0, it does nothing. But if you have state 1, it negates, it will give the 1, but it negates its value. So this is just a nice representation of our circuit. I have again run this circuit in our COSM simulator, and what we have got the probability of state 1 is 1. So let's see in terms of Hadamard gate. So now you want to make the qubit state in superposition, that is not 0 not 1, superposition of both. So I have created this circuit with Hadamard gate applied to the first qubit. Then let's see how does it look. What is the quantum state? 0.707 and 0.707, that is 1 1. This 0.707 is 1 by root 2. So if you take this outside, it will be 1 by root 2 times 1 1, which means you also have 0 state, also you have 1 state. So as you know, it rotates about z and x axis, that is this axis. It has rotated from 0 to superposition state, that is plus state, you can say. So you had the initial state as 0, and when you applied the Hadamard gate, you have got your new state of this qubit is in superposition. So here, as you know, the unitary operator for this is 1 1 1 minus 1. I have again run this on our simulator, and what I have got, I have the shorts 1000, and then for the 0 state, I have when I executed this on this backend for 480 times, I got 0 state, and for 520 times I got 1 state. So you can see the probability almost 48% you got the 0 state, and around 52% you have got 1 state. So what this x-axis shows is the number of possible states the circuit can have. So if you would have only 1 state, this would not be shown. So 1 with probability 1. So as this is in the superposition, you have 2 states, that is 0 and 1. So this is only for single qubit. If you have two qubits, the histogram, if you have two qubits, the histogram will be different, that you will see in the next session. Also for the S gate, I will show you the block sphere. I have applied S gate to the X, to the initial one state. So what happened? I had the initial state as 1, but I have applied S gate. Again, it is in the 1. Why? Because what S gate does, it rotates the state around Z axis. So this is already in the Z axis. So even if the rotation happens, it doesn't affect the state. So that is why this is in the, still it is in the one state. Same for S dagger. What you I have applied this S dagger to the state 1. Still you have got the one state because it is in the same axis. Suppose if you had if you had this initial state at this point, what it would do, what S gate will do, S gate will rotate 90-degree counterclockwise around Z axis. So suppose this was your initial, and if you apply S gate to the this state Hadamard, what you will get? It will rotate this state to 90 degrees. So you will get this state. So the vector would be here. So to actually see the effect, you can take this initial state to some other state other than Z axis. So again for T gate, as you know, T rotates it about Z axis to 45 degrees. So I have applied this T gate to state 1 again. What you'll get the same, because we are doing the operation around Z axis and our initial state is in Z axis only. So you cannot see the effect. To see the effect, make this state in superposition and then see the effect. Same with the T dagger. So this is RX gate. So I haven't actually defined the rotation gates, but what it is like P gate. What does P gate do? It asks the input as theta, and then it rotates around Z axis. So what does this RX gate does? It rotates the state of the qubit around X axis. So to define the RX gate, what you will do, you have to define the theta first. Theta, suppose let's say 3 pi. You have defined this theta as 3 pi. Then you have defined a quantum circuit with quantum and classical bit. And then you are applying the RX gate, that is QC RX dot RX with theta, that is 3 pi. And what is this 0? Second input is on which qubit you want to apply. So this 0 is on the 0th qubit I want to apply this RX gate. So when you draw, you will this 0 state, it will rotate around the X axis. So let's see how did this affect. So what happened? It was in the 0 state, and now it has rotated to state 1. What has actually happened? We have given 3 pi, right? So this is 1 pi, 2 pi, and then 3 pi. So that is why you got the output as 1. Same with the ry. If you apply ry with with the input as angle to the 0th qubit, you will get the state with rotation of this degree, that is 5 pi by 8 around y-axis. So you have got this. It is not inside the sphere, it is on the surface only, but it just looks that it is inside the sphere. It is just on the opposite side of the sphere. So it is here somewhere. You can change these gates, and you can literally see the effects of these rotations. How does this rotate? And same with the RC gate, what it does, it rotates around z axis. So you have applied 2 pi gate. Let's see how it looks on the block sphere. So it doesn't show any change. Why? Because already our state is on z axis. If you rotate any number of times, it will be on the z axis, because it will rotate uh, around itself. So it doesn't show any effect. So if you want to see the effect, take this in superposition, that is x, then rotate it. So it will rotate like this, that is around this z axis. So I have, if you want to, in general, if you want to make a U gate, you can also give the input as U. Suppose, let's say you have specific rotations you want to perform along x, y, and z. You can give the input as, I have already mentioned, that U with uh, theta, phi, and lambda being the rotations about x, y, and z. Right. So I have given the input here. I have created the quantum circuit, and then I have applied U gate, that is QCU dot U with pi by 2, and pi by 2 as theta, phi, and lambda, which are the rotations. On which qubit? On 0th qubit. So I have applied this U gate on 0th qubit. So what you will get? You'll get the output as this Y. So it is actually hard to imagine, these three gates. So mostly we won't be using these most of the times. If we want to, suppose, let's say you want the state and Y, this state, you will just simply use Y gate. So this is just a general way of representing any gate. That is, if you want have the specific requirement of rotating the gates into these angles. So this is one type of gate, U2 gate, when you have one angle fixed. It is U gate only, but you cannot change one angle, that is pi by 2. Let's say it is the same QCU2 dot U. I have fixed one angle, that is pi by 2. Then I have given other two angles as pi by 4. So if one angle is fixed, that is called as U2 gate. It is same as U gate. So here comes the phase gate, also called as U1 gate. So what input do we give for phase gate? We give theta, one angle, right? That is QC. I have created the circuit, then I have applied phase gate, that is QC U1 dot P with pi by 2 as angle, pi by 2 on 0th qubit. So you have got the block sphere as state 1. Why? Because what phase gate does, it rotates about z axis, so it doesn't show any effect. So this is the end of this basic qubit gates in Qiskit. So any doubts you have?
You please share the code. I'll also go through once because yeah, I have understood you. It was very, I mean, nice to hear all the Gates explanation. But then I think when I run it on my own, a few of my doubts will get clarified. That's what I understand. So can
Yes.
you please share the code?
Yes, yes, definitely. I'll share it soon. And also you can, manipulate all these
Values and then
terms,
check. Hmm.
theta, and then what happens when initial state is this, what happens if
Hmm.
you
Hmm.
apply Hadamard. Sometimes you will see the effect, sometimes you will see no effect. So why does this happen? Yeah. So
Yeah.
once you know all the gates do, you can use in the application you want.
Hmm.
Yeah.
Yes, that's what. Ultimately, we wanted to apply it in some kind of application. Fine. Yes,
Yes.
actually, yes, my students are working in quantum AI, so they are trying with quantum machine learning algorithms, particularly LSTM network and quantum neural networks. They are trying for a few domains, a few application domains. Medical imaging, one student is trying, and another student is trying in stock market prediction.
Uh-huh.
So they are trying to implement these and then trying to work in quantum machine learning actually. So yes, they had
Hello.
learned on their own. The students are really smart. And
Hello.
then yes, yeah, yes,
Hello. Yes, yes,
yeah.
ma'am.
Eh,
Ma'am, it's me. It's Rinjoy. Since you mentioned about quantum machine learning, so that's why
Okay.
I just thought to share my thoughts on it. So like because I'm also a supervisor. I am currently supervising a PhD student in the field of
Okay.
quantum convolutional neural networks, and I even have experience in working on quantum machine learning models and the projects, as you have said. Indeed, researchers are working on those kinds of aspects for
Yeah.
yeah, quantum neural networks, variational quantum classifier for
Hmm.
stock price and medical imaging.
Medical
Recently,
imaging.
yeah, COVID data was also classified with the help of quantum
Classified.
machine learning models.
Oh, great.
And people are
Mm-hmm.
also researching kernel based techniques for quantum machine
Mm-hmm.
learning that also has a
Mm-hmm.
huge potential. They are
Mm-hmm.
computationally expensive compared to quantum neural networks, but since they are able to support the larger Hilbert space, therefore
Mm.
if we really have a noise free quantum computer in the future, then
Okay.
we will be able to really utilize convert our classical data into quantum data,
Quantum
and
data.
really yeah, utilize those kernel methods which provide better accuracy than quantum neural networks.
Because with yeah, one of my student tried the same
Mm.
classification with the quantum neural networks, but then the
Mhm.
results were not that much good.
Yeah, yeah.
Classical was better,
Mm.
and then quantum was not that good. So we
Exactly.
were
Mm.
wondering, so where should we actually look into the use of quantum? So
I
all
can
kind of
completely understand.
classification
Hmm.
problems, yeah, we
Hmm.
can't take it and try, right? So we have to understand first of all what kind of applications should require when it comes to machine learning learning and deep
Mm,
learning. What kind of, even though I say medical imaging, many data sets are there. So,
mhm.
and the papers, whatever which have been already published, we are trying to implement the same and then check the results, how much we are getting, whether we are getting improved results or we are able to beat the classical one. So,
Absolutely,
that,
absolutely, ma'am. You're absolutely
mm,
correct, actually, and I agree with you. But, ma'am, you can keep your goals, and you can convey this to your students who are working, that
mm,
not
mm,
only to focus on the accuracy of the QML models.
mm,
Definitely, QML is a very new field of area. It's not even been a
mm,
decade. It's only about 6 to 7 years. Therefore, it
mm.
will be harder to get accuracy in the QML models, and classical has decades of research, so it has been
Yes,
much more
well
refined than QML.
established. Mm.
Exactly, well established. So that's why rather than focusing on the accuracy, it is more better now, to prove that, yeah, like QML architectures can exist, and with the proper quantum hardware, they will be able to provide speed up and advantage. So they can also, slowly start working on some aspects of complexity analysis or theoretical analysis of QML models. So if you see many papers, there also
Mm.
they have published results. There the accuracy of the quantum model, for some papers it is high, for some papers it is low.
Low.
But
Mm.
yeah, but what they have taken is, they have taken very simple data sets like black and white MNIST data set or fashion MNIST.
Ah,
Very,
yes.
yeah, very few people have actually tried with colored data sets or real
Mm,
world data
mm,
sets,
mm,
like
mm, mm.
unbalanced data sets. So
Mm.
those are very prominent areas of research, if your students would like to take care of that.
Yeah, sure, sure. So, can I have the mail IDs of you all so that if at all I require or my students require any help, they can
Yes,
contact
ma'am,
you.
definitely. Please feel free to contact me. I will be also taking a lecture actually soon.
Okay,
Yeah,
okay.
but at that time also, if you have any doubts, you can please definitely go ahead. I am
Yes,
already,
yes, sure.
as I mentioned, I am supervising a PhD student in Australia, University of Southern Queensland. She is in
Okay, okay.
Australia. Yeah, and
You are
the
working in IBM and guiding Australian students.
no, no, no. I am not working in IBM. I am working in Fractal AI as a quantum
Okay.
AI research scientist, and I
Oh,
have
great,
about
great.
all nearly 5 years of experience in quantum field, in
Okay.
QML, quantum computing as well, and even written a book last year. I
Oh,
have a
great.
Udemy. I have Udemy courses as well, internationally renowned there,
Yeah, yeah,
and
you know.
yeah, and
Mm.
people have found it to be helpful for preparing for the Qiskit exams as well.
Okay, okay.
So
That
yeah, if you
sounds
have
great.
any doubt, please feel free to mail me. I will be very happy to set up 1:1 discussion with you and your students as well, and provide any guidance you can feel like.
Okay.
Yeah,
Okay, that's great. That's great.
yeah.
Actually, the four students, whoever is here, are also really smart. And today
Mhm,
they weren't able to attend the classes because they have their exams. That's why. Otherwise,
mhm,
the students, whoever is here, they are all
mhm.
they are very good in basics, and they are also, as I said, working in quantum neural networks only.
Nice.
So yes, if once yeah, I'll check. If at all, in any session, we can ask my students also to share their insights or what kind of help they would require from you or other
Mhm.
peers with you. I'll check with them as well and ask
Definitely,
them to present their work so that will also give them a good experience how much they know and how much of work being done so far and what kind of challenges they faced in implementations. I can ask my students to present but I
definitely.
don't know whether you will be able to spare time.
Definitely, ma'am. Please let me know in advance.
Okay.
Anyways, lot of stuff is going on. Actually, I am
Yes, yes,
leading
yes.
this quantum grad. There is another global organization I'm leading. Lots of stuff
Mm,
already. But yeah, I will
mm.
definitely do my best to take some time for you and your students to help
Students.
you. I'll be
Thank
very
you.
happy to, yeah, guide them and have them published in some journal or, yeah,
Yes.
anything.
I'll make use of the mail ID. So instead of if at all we are finding difficult to meet
Mm.
online as we are all busy, so I'll mail the, and also
Yeah.
keep ask my
Mhm.
students also to directly contact you and keep me in CC. So that will also do good. I'll also
Yeah,
get
ma'am.
to
I'm
know.
sent in the Google Meet chat. Have you found? Uh, uh,
I'll check. I'll check. I'll check.
in
You have
the chat.
shared it.
Yeah,
Okay.
in the
Okay.
chat.
In the chat. Yeah. Yeah. I could
Yeah,
see.
yeah,
Yeah.
gmail.com. Yeah, yeah, yeah.
Yes. Yes. Yes.
Mhm.
I'll take the mail ID. Yes.
Mhm. I can also give my official university mail as well, just in case. Uh, uh, so this is also my official uh, mail address.
Okay.
For
Okay.
Voxen, I am a professor of practice, clinical professor of practice at Voxen. So I have
Okay.
basically academia collaboration, as well as I have industry collaboration. So for
Oh,
both
great,
of the
great.
places, I do, and I lead separate research. So it at QuantumGrad also, I think I will be doing something, not now, maybe after a few months. Currently,
Oh,
it's
fine,
already,
fine.
yeah, quite tight schedule.
Yes.
Uh, but yes, please feel free to, like, copy all your emails to both the email addresses, because I keep checking them regularly.
Ah, sure, 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 sir, sure. I'll
Definitely,
mail.
definitely.
I'll. If you are interested to be adjunct of our university, even I can very well take it forward and recommend you to to our IR section.
Oh, that is
Uh,
really nice. But I need to first know what are the time commitments, because like here
no,
at Voxen,
initially you
I'm just
can be
teaching a
the
subject
yeah,
actually. Yearly
yeah, yeah,
once I
yeah.
teach a subject.
Yes, yearly once only, and
Mm.
during December or during our vacation time only, we usually conduct adjunct courses by